Science time. Let's, the camera is not going to be able to see over here. Well, I'll just say it. The objective today is discuss DCI, comma, CCC, comma, and SEP. Raise your hand if you have heard of any of those before. You all should have. I'm going to say that, and that'll make you feel bad when you don't raise your hand, but raise your hand if you've heard of any of those before. Perfect. Good. Raise your hand if you've heard of this. This was up on the board when you came in. Have you heard of that? No. This stands for Nebraska College and Career Readiness Standards for Science. This is the state standards that govern not only what I teach, but how, not really how I teach, but the methods that I teach. These are the state standards. We did look at them, I was going to say yesterday. That's not true. I didn't look at them yesterday. We did look at them together on Thursday, I think, when we looked at the syllabus. They are linked in the syllabus. These are how I know what we should be learning in science. They can be how you know, but you can also just trust me. Today we're talking about DCI, CCC, and SEP, which are segments or parts of the Nebraska College and Career Readiness Science standards for science. You don't have to write this down. You aren't really responsible to know about the standards. I am, and then I teach it to you. Does it say 937 on the period 2 thing? I think it does. Okay, nice. Okay, perfect. Good. So we got plenty of time. Okay. So what are we learning about in here? I mean, in this room, what are we learning about? Science. What is science? Let's think of a definition. Science is math. There's the same thing, we just call them to. No, what is science? What is science? It has math. It can have math. Is it math? I wouldn't say so. Does it include math? Yeah. What is science? Just think of a definition that kind of works for you. Is it, well, okay, I'm going to say one that it isn't so that you don't say this one and then feel bad when I say it isn't that. It is not just, let's put this, not just a body of knowledge. What are some science facts, like that we traditionally associate with science? Yeah, like we learn about, like, these are the different kingdoms of life. These are the different phyla of the animal kingdom. These are the different classes of the phylum Chordata or whatever. We do learn some facts. These are the planets. Mercury, Venus, Earth, Mars. I forget the rest. Doesn't matter. No, I'm just kidding. I do know them. But that's not what science is. Science is not just the facts that we know about science. Why do we have to know any facts for science? It just helps us communicate, really. Part of what we learn, especially what you learn in elementary school about science, is the things that we talk about in science so that you can communicate more effectively with the science words. But it's not just that. In fact, I wouldn't even say it is that at all. That's not what science is about. What is science about? Well, we have a scientific method. You guys know about the scientific method? Why do you say you don't remember, Miss Benson? What do you mean? You don't remember what? Because you're thinking of, like, here are the 12 steps of the scientific method, or here are the 6 steps of the scientific method, right? You're trying to remember those, like, ask a question, create a hypothesis, make an experiment. You're trying to remember those. But I'm here to tell you, and this is, I think Mr. O told you this last year too, that's not really what it's about. The scientific method is a lot easier than that, I think. For instance, what you learned in elementary school about the scientific method probably had, not only was it different, but it probably had a whole different number of steps than what you learned in junior high school. And that had a whole different number of steps than what we learned in high school when I used to teach it this way. You can find, if you look on Google, you can find the scientific method has 4 steps. The scientific method has 9 steps. The scientific method has 6 steps. I'm sure you could find one that has 12 steps. I'm sure you could find one that has 20 steps. Why are they all different? What does that tell us? The fact that they're all different and the people still use them tells us what? It doesn't have to be that way. It doesn't have to be that way. The scientific method does not have to always include, you must ask a question. You must form a hypothesis. There's a poster on the door in the lab that maybe you can kind of see. It's called Scientific Method. It looks like it has 1, 2, 3, 4, 5. That one has 6 steps. I don't know what they are. I can't see them from here. I can see the second one is hypothesize. Do we always have to hypothesize? Not really, and there are different kinds of scientific method for different situations. My point is that science is a really more of, is it a body of knowledge? No. There is a method, though, to it. I would say it's more of a, science is a way of understanding the world. When I was in chemistry, my chemistry teacher, called Mr. Jones, said about the scientific method, he said, if you're a smart person and you want to understand the world, you observe things and you ask questions about them and you maybe experiment with them and you do research, basically the scientific method. If you're a smart person, you do those things. If you're a stupid person, you eat it. Like this is how smart people understand the world. You just do these steps. Let's make an example here. What if, who's friends in here? Who has a friend? Great, okay, one person has a friend. Miss Riggs, who is your friend? Miranda and Fia are your friends. Let's say you three, the three of you, are walking from here to Wesco at lunchtime. That could probably happen, right? So far, this is a realistic story. You were walking from here to Wesco at lunchtime, and what? What? You're walking from here to Wesco at lunchtime, and you see a snake. And are you scared of snakes? It doesn't really matter. Okay, so you are interested in the snake. You walk over to the snake, and you might want to find out what kind of snake it is, right? What would you really do? Like, if this was your story, what would you really do if you wanted to find out that kind of snake? Okay, so you already know about snakes. So what have you done there? Okay, so the first thing you did was you saw a snake. So you made an observation. Okay, what did you do next? You picked it up. You're going to look at it, and what are you going to do with that looking at? Probably, yeah, you're probably going to inspect it, so we could put that up here, inspection. Probably, I would say Garrett is right. Probably you're going to look it up on your phone. Someone in the morning said Google. I don't really love that as a verb, but you are going to Google it. Probably. What is that called? What could we use? What's a nice way of saying that? Research. Yep, research. And then when you find it out, what are you going to do with that information? Yeah. Okay, so you might have an action, but what are you going to do? When you find out what it is, you are going to say it again, Cody. Tell everybody. What do we call that in science? Share. That's true. No, there's a better word than that we actually use from the scientific method, which is almost always part of the scientific method. Communicate. And so you have done the scientific method. My point is that you do this in your daily life without even ever really thinking about it. You certainly did not. Let me tell you. You did not fill out a worksheet where you put, what is your observation? What is your hypothesis? What was the experiment? What is your conclusion? What is the analysis? You did not do that, did you? But you still did do science. My point is that you do science all the time. You are a scientist because you use science as a way of understanding the world. Your job might not be scientist. In fact, your job almost certainly is not scientist because you're 13-year-old girls. But you still are a scientist. You use science to understand the world just when you do things like that. Let me give you another example. You guys don't use Facebook because you're not 62. What do you use? What is your social media? Some of you who have a social media. Do you use Facebook? Yeah. Oh, okay, because you are 62. So you're scrolling through Facebook. Maybe this is not an example that really applies to you because you're so young. But let's say you're scrolling through Facebook and you see your ex-boyfriend and he's got a new girlfriend and you think, who is that girl? So you're doing the scientific method. I'm telling you the dang truth. When you go and stalk her on Facebook to find out who she is and about her life, that is the scientific method. You are using the scientific method. And remember, if you're smart, you use the scientific method. If you're stupid, you eat it. You just like, oh dang, my boyfriend's got a new girlfriend. But if you really want to find out, if you really want to find out, you are using the scientific method. You are a scientist. Even in as stupid as an example as that, you are a scientist. You are doing science all the time. This is how you learn about the world. The reason you're in this class, and the reason it's important for you to take this class, is because my goal and what I'm trying to do is to teach you how to do this better, to be more efficient at the scientific method. We do use things in the fat body of knowledge. We do use things in this to kind of have things to talk about. Like we'll talk about forces, we'll talk about space, but those are vehicles that we use to convey the scientific method. We're really focusing on how we do things in here, how we understand the world around us. most of your quiz and test questions, this is probably the way it was last year, most of them will be having you do things like, it'll say like, Sarah is a paleontologist and she discovers this new species of dinosaur. Looking at these bones, which of them is the best inference, or whatever. But it'll be an example of doing things. That's what science is about, is learning about the world. It's not about just memorizing the order of the planets, memorizing the periodic table of the elements. That is not science. These are tools that we use to do science. These are things that we talk about in science, but the scientific method is what actually makes up science. And you're doing this all the dang time. So don't come to me saying, when are we ever going to use this? Because more often than not, what we're learning about, the content, we're going to get to this in a second, but the content, periodic table, planets, whatever, what we're learning about is being used as a vehicle to make you better scientists. Does that make sense? So it may be true that you are never going to see or use the element hafnium in your entire life. But we can still use it as examples to make you a better observer and inspector and researcher and communicator and experimenter. Because you do experiments, whether you think about it or not. Do you take my point? Do you have questions about this before we move on? Questions about scientific method. This is not the hill I'm willing to die on. If you find a piece of evidence that says, oh, actually, Mr. Keim, Isaac Newton said there are only 5 steps in scientific method and they always have to be, I'll be like, okay, whatever, that's fine. My point is that this is how I think about science. And I think you are a scientist. I think you do this all the time. Maybe it's not structured. You're certainly not doing clinical labs all the time. But this is still a scientific method. And when you do clinical labs, that might be a 1,000-step scientific method, but it still fits into these little bubbles. I would say the scientific method can be broken down like this. Observation, inspection, conclusion, or communication. Let's put communication. This one is the key here. This is where it can differ. So we have something we want to learn about, observation. And we're going to do something in order to learn about it. Maybe it's research, maybe it's experiment, maybe it's even very well-structured clinical trials like they do for new pharmaceutical drugs or the coronavirus vaccine. But that's all in here. And then they communicate that to people. So this step might be broken down into 50 other steps, but it's always the same things. Something we want to do, some observation that we make about the world, some phenomenon. Have you heard that word before? Some phenomenon, something that happens in the world that we want to know more about. We do some inspection, usually research, I would say, but maybe not always. And then whatever we do, we communicate. What might the communication look like? It might be Miss Riggs telling her friends, this is a bull snake, and then putting it down. That might be the communication. But it also might be a 65-page academic paper that took 3 years to write and is written by 15 PhD people, and they have a 25-page long bibliography of their sources cited. It might be that. That's communication too, though. Obviously, one of those is more scientifically valid. Like your observation, this is a bull snake as a 13-year-old girl. I'm not trying to put you down, but that's probably not as scientifically valid as the 56-page paper about the mechanism of the cytokines in the brain or anything like that. Do you understand? Like there could be different values to the science, but it's still science. You're still a scientist. You're a good scientist. Keep up the good work. Do you have questions about this once again? Let's move on to actually fulfilling the objective. This is my philosophy of science. You might hear it differently from different people, but I think there's the kernel of truth here is going to be found to be true anywhere you go or anyone you ask. What's happening if I'm erasing the board and you haven't written this all down? What could you do? Yeah, watch the video. Not now because you don't have your Chromebook. Obviously not now because I'm still up here. But also not today because you don't have your Chromebook. But eventually you can rewatch this. Also, what's in your notes is up to you. But I would really encourage you to write down, to the extent that you write down anything, I would encourage you to write down the things that I write and the things that I specifically tell you to write down. Like if I say write that down, then probably write that down. But I would love to see your own little thoughts in your notebook. That would be great. I would be very happy with that. So part of the Nebraska College and Career Readiness Standards for Science is that it's broken into 3 what are called dimensions. In fact, our textbook is called HMH Co. Dimensions, and these are the 3 dimensions of science education. DCI, CCC, and SEP. These are not just made up groups of letters. They stand for something. DCI stands for can't remember right now. CCC stands for cross-cutting concepts. And we'll go into more depth in these in a future video. I think I might just have you watch the one I did last year because it's the same stuff, but we'll see. And then SEP stands for science and engineering. Put too many E's in it, practices. I'm going to leave it though because I make mistakes. DCI is disciplinary core ideas. Let's start with this one. What does the word disciplinary mean? I mean, there's a couple definitions. What does it mean to you? Okay, yeah, what's disciplinary mean? That's what I asked you. Okay, yes, relating to discipline. So what is discipline? They're different. I like that. Say it.
Held accountable.
Okay, that's better. You're going to say trouble, but held accountable is better. So there's a kind of discipline. Like if I were going to discipline my child or discipline my students, it would be a corrective thing. Like I would be just spanking the crap out of them. No, I'm just kidding. That's not how we do it here. But that is a kind of discipline. But to correct something that's wrong is a kind of discipline. But that's not what we're talking about here. We're talking about disciplines in that. Have you ever heard of the different categories of a field being called disciplines? So like what we're going to get at here is that within the field of science, there are disciplines of biology, physics, chemistry. You've heard of these things, right? We could call those disciplines, and that's what this is relating to. So these are the different, I'm going to call them subjects of science. And these core ideas are the things that we need to know in order to be good at these different subjects of science. So things like, for example, if the subject was physics, some disciplinary core ideas, the core ideas that we have to know to be good at physics are things like forces, energy, etc. Right? What are some disciplinary core ideas for biology? What are some things we have to know to be good at biology? Cells. That's the main one I was thinking of. What else? I would say cells, evolution, growth, reproduction, nutrients. Yeah, those are all things we have to know about to be good at biology. So within the disciplines, within the subjects, there are always going to be some core ideas. And this is what we would normally call the content of a science class. This is the body of knowledge that I was talking about. The science isn't just. Science isn't just these things, but these are things we're going to talk about all year, and these are the main things you're going to be tested on, because these are the things that, and traditionally, these are the only things you would learn. But now we got these other two whole dimensions here. Cross-cutting concepts, what does it mean for something to cross-cut? Yeah, that's exactly what I'm getting at. You skipped a couple of steps for me, but that's okay. These are things that go across subjects. So they're concepts that go across subjects. So something that applies not just to physics, but also to biology, or not just to chemistry, but also to physics. And in fact, they all apply to all the sciences, and you can see them up there. Let's just list them real fast, and then we'll talk about them more in depth, or I might have you watch the video. They are patterns, according to your book, they are patterns, cause and effect, scale, proportion, and quantity, systems and system models, I'm going to put little hyphens before each one so you can tell when a new one begins, energy and matter, structure and function, question? Question? Okay. Stability and change. And I shouldn't have used that tone of voice because that's actually the last one. Stability and change. Do you think there are more things that apply to all the different kinds of sciences? Yeah, but I think any of the other ones that we came up with would either would not apply to all of them, or they would be kind of a category within these. We'll talk more about these in depth later, and we'll also read those. And like I said, we might just have you watch the video. But these are the things that apply to all the different fields of science. Let's do an example real quick. Systems and system models. If I said system, what would you think of first, maybe? What are you thinking of first? What kind of system would we talk about science? The solar system. Is that what you said? The water system. Okay, let's use that one. I thought you said solar. I gave it away. I hoped someone would. The water system. So there's a water cycle, right? There's a water cycle. The Earth has a system of water on it. What else? What other kinds of systems are there? The solar system. What's another one?
Body system.
Like what? What name a specific one?
Human.
Okay, but name a specific system within the human body.
Digestive.
Digestive system. Okay, so we have 3 examples now. Water system, solar system, and digestive system. Are those all in the same subject of science? No. But they're all kinds of systems, aren't they? They're all things that are working together. Maybe not working. Working implies that they have some kind of agency of their own. They can think or whatever. And none of those do. But they're all things that are functioning in the same, I'll try not to use the word system, in the same realm of existence. The solar system is several planets and a sun, and a star and other bodies orbiting each other held together by gravity, but they're all interacting with one another. The digestive system is several different organs within the human body, but they're all interacting together. The water system is several different sources of water, but they're all interacting together. Do you see what I mean? So they're different subjects, but this concept applies to all of them. Does that make sense? And that's true for all of these things. We'll talk more about them, or like I say, watch the video in the future. And then this one is probably, I mean, they're all important. This one might be the one we talk about the most, but this one might be the one that the standards focus on the most. These are the things that you are actually doing for science. They are asking questions, is this an important thing for science?
Yes.
Heck yeah, I would say heck yeah. Asking questions, developing models. Does this mean just like building a model airplane or a model solar system? No, it doesn't mean that, Gary. And when I ask questions like that, the answer is probably no. This does not just mean that kind of model. A model in science, and we'll talk more about this in the future several more times, but a model in science is a kind of a basic way of representing a subject that we know has inaccuracies, but it's still useful for its intended purpose. So developing models, planning and carrying out investigations, math. There's your math. Whoever said math earlier when I asked what is science. Was that constructing eggplants? That can't be right. Constructing explanations and designing solutions. Explanation, we'll put that. I like this one. Argument, but it's not just argument from evidence. And this does not mean yelling at each other and throwing plates and stuff. It's not that kind of argument. It's mean you're making a case for something, a claim that you have made, using evidence to support it. And the last one is communication. Do you see overlaps between these and what I called the scientific method? Yeah, these are all things that we do in science and in engineering that make it so that those subjects can be understood and conveyed. Do you have questions about the 3 dimensions of science education? Can you think of more examples of these? You don't have to, but can you? If you had to sit down, like if your homework were to sit down and think of more examples of DCIs, could you do that? Yep. Could you think of examples within these categories? Like, could you think of examples of patterns that apply to every different subject? Yeah, of course you could. Could you think of situations in which we would use these things, in which we would do these things? Yeah. You don't have to. That's not your assignment. But as long as you could, that's what I'm worried about. Do you have any other questions about any of this or about the scientific method or why we learn science? The objective was discuss DCI, CCC, and SCP. Did we do that? Yes. Any questions?